Okay, so yeah, thank you, Raj, for the introduction. So my name is Zhilin, and I'm going to talk about smart HPC through intelligent scheduling. So as Raj pointed out, I have been working in a close collaboration with the Cobalt team, a scheduling team at Argonne for quite a while. And in this talk, I will present my research at addressing several various scheduling challenge. And this is the outline of my talk. I will talk about I will start with what is a smart HPC, and then I will talk about what is intelligent scheduling and why we need to do intelligent scheduling. And then followed by two major projects I did in the past few years. And finally, I'm going to conclude my talk with some open issue in this field. So first, let's look at what is happening in HPC. HPC workload are changing. So HPC has ushered in a new exascale era where the traditional scientific workload has converged with the machine learning, deep learning, big data workload. Now we start to see explosion growth of the adoption of AI and machine learning, not only in terms of the number of people, but also in terms of the number of cycles that are being used for machine learning and AI application on the big machine. And one of the things that we have been seeing in the past is that HPC users are using AI or machine learning for their data analytics, for modeling and simulation. And meanwhile, we also see that supercomputer has been proved suited to do a lot of AI applications. For example, a few years ago in ICPP conference, the best paper is awarded to the group which has showed that if they use the machine, the Stampede 2 at the attack, they are able to reduce the training time from days and hours to minutes. So this workload convergence impact every aspect of HPC, especially the system software aspect. Now, what happened in the other part of HPC? HPC platform also are changing. So as the system and the chip architecture shifted to a heterogeneous world. So as shown in this figure, I just give a few examples. For example, that Intel has stated that there will be a hierarchical of heterogeneity in their future system. This is a result of the shift to the data-centric application and a lot of new workload, different workload. And the AMD's vision for exascale computing also hinge on a heterogeneous approach based on this called exascale node, which actually is composed of integrated CPUs and GPUs. And at the left corner, I also show this Aurora architecture. Aurora is going to be the first exascale computer at Argonne. So it's going to incorporate a number of technological innovations. One of them is that it's going to be a integrated Intel Xeon Scala processor accelerated by Intel Xe computer GPUs, okay? So what we are looking at when we look at the changes in HPC, as the application, the workload become more diverse and the platform become more heterogeneous. And it is become very essential to incorporate a smart grid. So we envision that future HPC will become smart HPC. Okay, smart HPC. So what is smart HPC? In a smart HPC, information about system resources and workload will be automatically gathered analyze, and act on for improved productivity. In productivity include performance, resilience, energy efficiency. In this design, in a smart HPC, they should have many improved components. In here, I put two major components. One is active learning. Active learning means that it's going, so this is a component in HPC which is dedicated to extract valuable performance, energy, resilience, all these workload and platform resource information from online learning, and then extract important information for workload and for system management. And then the second important part of smart HPC will be the intelligence runtime. Intelligent runtime means that they're going to do adaptively improve their action in response to changing environment. In this particular content, I will focus on batch scheduler. So when we look at all these new components, this new component is supposed to imbue HPC with a higher order of intelligence by providing both forward control and the backward feedback. So here, this figure shows the solid arrow shows the forward control, and then this dashed arrow shows backward feedback, okay? And now we go to this batch scheduler. So all jobs, all HPC actually use batch schedular for user to use the shared limited resources as shown in the bottom of this slide. User actually submit their job to a queue manager, a job queue, and batch scheduler is a system software sitting between the workload and the computing platform. It will decide when and where to execute the user job on the platform. So the batch scheduler has been used a number of terms. It also known as job scheduler, class scheduler, workload management system. And currently widely used scheduler include Cobalt, which I have been working with, and SRMPDS, and there's a number of others. When we look at this design, so you will see that existing scheduler are actually fundamentally designed for the traditional paradigm. When we say traditional paradigm, means that they are target a few large long-running jobs on actually a homogeneous job on homogeneous platform. So we already see that HPC is changing in terms of both workload and the platform. Okay, so there is something happening there that we need to make change to make it smart or make it intelligent. So one thing that I often being asked by different people is that when you say scheduler, what do you mean? So in my point of view, scheduler is a very broad term and has been in many different content. So I usually classify scheduler into three groups. One, I call it application level scheduler, which focus on specific workloads, such as if you use a schedule specific for workflow, that I call it application level scheduler. And the second group, I call it OS level scheduler, which usually focus on the resource allocation on a specific compute node, for example, Linux scheduler. And here I'm looking at the batch scheduler or other class or job scheduler as a system level scheduler, which are focused on allocate or management resources belongs to I have been working with Cobalt team at Argonne. So what is Cobalt? Here I show the location for this Cobalt software. Cobalt is an open source and component-based job scheduler. And it started probably around the 1990s when the ALCF was formed. Then the only scheduler at that time that support the bridging system was the IBM load leveler. However, it couldn't support other type of OS. And then ELCF decided that they are going to maintain a new scheduler called Cobalt. And this Cobalt going to have some, this new software going to enforce a specific batch scheduling goals and constraint at ELCF at their specific site. As I said, Cobalt shown in this slide is a component-based design. This one shows what are the major components in the Cobalt. They have this portal and then resource manager and then job scheduler and also the logging system. So Cobalt use this component-based design. This actually allow them to easily placement some key component if they see the needs. So in order to do smart HPC, we need to have a few, as mentioned in the previous, we need to have a few major components. One of them is called intelligent scheduling. So intelligent scheduling, why we need that intelligent scheduling and what is intelligent scheduling? If we look at the current batch scheduler, they all concentrate on CPU utilization and make allocation decisions solely based on application processing footprint. This become complete at odds with the emergent hybrid system architecture and diverse workload requirement. So intelligent scheduling means that the scheduler can automatically allocate workload to the most suitable resources available. So an intelligent scheduler must consider not only the high increase in the overall system heterogeneity, but also the expected diversity of application characteristic. In addition, as we are moving toward exascale computing, cross-cutting issues such as power efficiency, resilience will become, actually already become the first class concern in addition to the pursuit of our performance. So this figure shows some of the major components that my team and my collaborator has been pursuing in the past few years toward intelligent scheduling. And I'm going to go, I won't be able to cover every aspect, so I'm going to start with this power awareness. Okay. Oh, by the way, if anyone has a question, feel free to interrupt me. I will be happy to answer. So let's look at the power awareness. So if we look at the power efficiency, everyone knows that when we go to larger or complicated exascale computing, power becomes the first class concern. And the existing study has been mainly focused on energy efficiency or energy proportional hardware design, dynamic voltage and frequency scaling. And also there are some study focused on shutting down unused or unnecessary hardware component when system utilization is low. There are also people work on thermal management. There are also people work on power aware scheduling for some specific application or workload. So in our design, we're also focus on this power awareness. However, when we look at the problem, we focus on scheduling, means that we are focused on scheduling design to control the power consumption of the entire system under a user-defined cap. So the goal is to control system-wide power consumption, not a specific. When we design this power-aware scheduling, we have two principles in our mind. One is that to make sure our design is applicable to general HPC application. So in the current design, there are a number of research on power-aware scheduling. Some of them targeting multiple jobs, meaning that the job size can be dynamically decided by the scheduler at job allocation. For us, when we design this, we realize at ALCF, most of jobs are rigid jobs. So when we design our scheduling method, we make sure that we don't want to put any extra requirement on the workload, and the design should be applicable to general HPC application. Second principle, HPC systems require very significant capital investment. Hence, making efficient use of a system is of paramount importance. So on our design, we make sure that our work enforces a power cap while maintaining high system utilization. We want to minimize the impact on system utilization. So because of these two principles, we end up with three major components in our design. So we're going to start with these three components. So first, we look at the power. What are the job profile in HPC? So at Argonne, at the ALCF, a couple of years ago, when we started this project, they use a bridging queue system. And bridging queue system have environmental monitor capability. It periodically sample and gather environmental data. Environmental data means those sensor information that sensor can collect, such as voltage, current, and fan speed information, and then dump this information into an environmental database in a specific interval, such as 4 minutes, or you can tune down the interval. And then what we did, we first start to look at what are the power profile of mirror. So we are able to pull the data from this environmental database for the whole year in 2014. And then we look through all the jobs submitted within this year. And then this table shows the job power profile. So power profile is in the kilowatt per rack, okay? And then this shows the minimal job power profile requirement is 36 kilowatt per rack. And we also shows the mean, maximum, what are the percentile, and what are the standard deviation. When we look at this table, a very striking observation that we made is that if you look at the minimum and the maximum, HPC job, we notice that HPC job has a very distinct power profile, and the difference could be as high as 4 times. Then we start to think whether this can be used to design our scheduler. And then this two figure goes a little bit further to look at what are the specific, why there are so many different change, why there is a high power profile difference within HPC job. So usually in HPC, in the system, the user, we have user belongs to project or group. So we randomly pick up 6 project, which is the left figure. We randomly pick up 6 project or group and look at what are the jobs belong to this project, what are the power profile for this project. So as you can see, each project has a very distinct power profile. And then on the right, we look at for a project, the same project, what are the user belongs to this project, whether they have the same or different power profile. In this figure, look at power profile for a given project, and we random user. So if we combine two, not only the job have a distinct power profile, the project they belong to has the same characteristics. So leveraging this observation, we start our design, okay? So I notice my network is not stable. Okay. So So what are our designs? So on the top, I show this traditional HPC or batch schedule design. User submit the job to the queue. And then if I use a FCFS, first come, first job, first serve, then job going to pull out of the queue one by one and allocate it onto the system. Of course, backfilling is commonly used to address this utilization issue. This is a traditional batch scheduling design. It has been a default design in almost all current batch scheduler on production system. So what we did is that we follow almost the same design. However, we add two major components. One is a dynamic learner. The other one is a power-aware scheduler. So the difference here is that first, we add this dynamic learner. This one going to periodically get power profile from the underlying system power monitor tool. For example, I can use the database collected from the bridging system, or if you have any profiling tool that you can pull this data by the learner. The learner going to estimate job power profile. And then the next major component is the scheduler. Scheduler, instead of a select job from the queue one by one, we are going to use a window-based design. Means that we'll follow the job order that enforced by the site. For example, I'm going to collect the first 3 jobs from the queue, and then I will decide one of them or maybe a couple of them should be allocated onto the system so that we can still maintain high utilization, but we can control the overall system power consumption within some cap. That's the overall design. So let's look at a very simple example to understand the concept. Assume that we have a system. The system has 6 rack or 6 node, whatever you think about is a unit. So assume I have a system with a 6 rack, and I enforce a system-wide cap as a 230 kilowatt. Now, if currently I have 4 jobs in the queue, and this is the head of the queue, and then each job have different requirements, such as the number of CPUs and what are the power profile. Now, if I use a traditional first come, first serve, it's going to pull the job from the queue one by one. So it's going to select the J1, the J0. If you use this type of scheduling, you're going to have a 2 rack unused because you won't be able to put more job into the system due to the power cap requirement. However, if you look at this design, our scheduler going to select the J1, the J2, as this design going to maximize utilization, still keep the system power profiling, power requirement under the cap. This is design. Then this is a simple principle behind our design. How can we enforce this design? So it's going to need a number of components. One is a learner. This learner going to take power data from any available power monitor facility. And at each scheduling instant, the learner has 2 tasks. One of them is to estimate peak. We focus on the peak power requirement of each job in the queue. And also it's going to calculate the available power budget for incoming job. By doing so, they need to know what are the current power profile, power usage of the running job. That's the learner. Now, this actually ends up with a number of possibilities. First, if a job is new, then we don't have any power information. What can we do? So we set the job usually. If we don't have the information of the job, but if we have the information of the project, then we are going to use the project peak power profile for this job. If we don't have any information, then we use the maximum required load power for the job. Now, if I have a previous power data available, then we'll use the job's previous profile. So as you can see, this is based on this historical information build up and active learning during when new job coming. So this learner supposed to constantly update the power profile, and in order to address those statistical variation, we use this called the two-sample t-test to make sure that the means of two populations are statistically different from each other. And then the next part is the power-aware scheduling. So now you estimate the dynamic learner learns the existing system power profile and then estimate what are the incoming job power requirement. Then we formulated the problem into a 0-1 knapsack problem. So instead of pull the job one by one from the queue, we look at the window of jobs. And then we'll formulate it into some kind of optimization problem. Our goal is to try to maximize the system utilization. When you maximize that, you want to make sure when you pull a new job into the system, you want to make sure it won't go beyond the system available resources. And that we want to make sure that the new job, when you allocate the new job to the system, the power profile won't go beyond the cap. PB means the power budget. So this is a design, and then we use a dynamic programming to solve the problem. So there's a number of issues here, actually. One thing is how large will be your window, right? Because if you have a long window, then of course you can have better optimization. But if you have a smaller window, then you have small space to optimize the problem. So in our experience, based on all kinds of workload at different system, and also we look at some other system from Lawrence Berkeley, we find that the window size in general, in typical current HPC is ranging between 5 to 20 will be the reasonable size. This size means that we can have a reasonable improvement. We also can make a quick decision within seconds. Okay, so in order to evaluate this design, we use this stream version of CQC. CQC is an open source Python-based scheduler event-driven simulator. And we have been designed and maintained this scheduler simulator for over 10 years. And it's free, everyone feel free to use it. So we have been tested and evaluated the scheduler with system real trace, and also evaluated with other scheduler on in the market. So what we did is that we collected a mirror log from 2014, a year log. We look at both job trace and their power data. And then when we evaluate our work, we focus on both learning accuracy. Learning accuracy means a percentage of job with low power profile. We also look at the capping successful rate. Means that proportion of a scheduling interval where power is under some cap, and then we also look at the scheduling performance. This is a learning accuracy. Learning accuracy is a proportion of the time that we know job power profile. So we start from the January 1st. At the beginning, we don't know anything of the job. So the learning accuracy is low. However, when we continue monitor power profile, we start to know the system job profile. And then so the key observation after 26 days a month, then we pretty much know most of the job profile on the system, okay? And then the second part is the capping successful rate, means that we look at interval, what the proportion of the interval that we are able to maintain the job profile within some cap. So in this figure, we show for the whole year trace. During this whole year, so there's so the Y direction represents the power usage. And there's a two curve in the figure. The green one represents system power utilization without any capping requirement. And then the red represent the system power usage after apply power aware scheduling. Okay, so you can see, so if we don't cap the system, so the maximum power allowed power consumption is about 5 megawatts. So in this example, we put that cap, which is 3 megawatts, is about 60% of the maximum. Now, if you go through the whole design, the whole year evaluation, 99% of the time, we are able to cap the system power within this 3 megawatt, which is 60% of the peak power. There are some exceptions here. The exception, so why there are some exception? So power cap is set to a low value, okay? Now, there are some cases, none of the job in the scheduler, in the job queue can be allocated onto system because each one of them, each individual of them will violate the power cap. For example, if I have this whole system job, this job, if I allocate it, I'm going to violate this 3 megawatts power cap. So there is a lot of alternative for these cases. In our design, we choose to temporarily violate this cap so that we can make some whole system job to go outside of the, to be allocated instead of waiting forever. We also do a more evaluation. For example, we can change the system-wide cap dynamically at the runtime. For example, we start the system with 2 megawatt, then we increase for 3 megawatt, and then we go a little bit over 4, and then go back, and then check whether our design can cap the system power within the allocated power cap. And the observations are about the same as the single cap, which is 99% of time we are able to do that. Then we look at the scheduling performance, which is a major part that we need to look at. So we look at, in here, we look at average job wait time. So this figure shows the relative change on job wait time normalized to uncapped first come, first case. If I look at this figure, so the further away from 0, the greater the relative change to the uncapped system. So in other words, closer to 0 means better because we are looking at wait time. In this figure, we have 3 different plots. If we have a cap at 2 megawatts, 3 megawatts, 4 megawatts. So we basically start from a heavily capped system to a lightly capped system. And then in each plot, we have naive capping, means that we use a naive way that adopt in most current production scheduler, which means, for example, if you use FCFS, I'm going to look at the incoming job, and I will look at its CPU requirement and its power requirement, and then decide whether I allocate it. So the green one is our capping. So the general observation is that naive method always works on average than our design in terms of average wait time. Of course, when system has a very relaxed or light power capping, then the relative change to user average job wait time, of course, is small. And then we also look at the utilization. Same thing, this is a relative change on system utilization. We again look at the different cap and combine and compare with naive capping. Again, close to 0 means better. Of course, when you have a power capping, this system utilization going to impact a little bit. And then we will see how much capping will have on the system utilization. So in general, observation from this study is that when the power cap is about 8%, then we observe minor or no degradation in scheduling performance. That's what we have so far for this design. Any question? And Zhenchun, when should I finish?
I think you can still go on, Ziling. Anybody has any questions at this point? Looks like not. You can keep going. I think we've
10
scheduled
minutes
it
or 15?
till the top of the hour. So yeah,
Okay.
I think you have.
Okay. Second part, I'm going to discuss another project we have been working on toward intelligent scheduling. That is a multi-objective. So if we look at the current HPC system, because of diverse workload, we see this change in the architecture. For example, to meet the intense I/O demand from emerging data-intensive application, burst buffer is commonly deployed in production supercomputer. And this figure illustrates the architecture from the Corin machine. It's a CRE-SC machine at Lawrence Berkeley, okay? So now, as we mentioned in the beginning, current batch scheduler focus on CPU or CPU-oriented scheduling. However, with this new schedulable resources available in production HPC system, then it is crucial for HPC scheduler to schedule a user job, not only based on CPU, but also based on other schedulable resource, such as a burst buffer in this case. So how to handle burst buffer in job scheduling? So if we look at the existing solution, we summarize all the existing solution into 4 different approaches. One is called the naive, which is supporting the SLAM. Basically, you run the job, they're looking at the job in the schedule, in the queue, and then they will allocate the job from the wait queue in the sequence until either CPU or burst buffer is exhausted. Another approach is called constraint and wait, and the third one is called weighted. Both belong to optimization method. These are 2 optimization approach to solving multi-resource scheduling. So in the constraint method, they optimize utilization of one resource and treat other resources as constraint. That's why it's called constraint approach. And then third one is called weighted. In weighted means that if you have a multiple resource for scheduling, they will combine the utilization of all these resources or objective into one through a weighted sum. That's why we call it a weighted approach. In data center, the company use approach called bin packing. So they basically select the big means that in terms of CPU or burst buffer or any others iteratively. It's a heuristic method. These are 4 commonly used approach in the existing batch scheduler or cluster scheduler. What are the problems? Are they fine? So we look at the example first. Suppose we have a system with 9 CPUs. We also have 9 units of burst buffer. And then we have a number of jobs in the queue. Let's say if we have 4 jobs in the queue, and this illustrates for each job, what are their CPU requirement and burst buffer in requirement. Well, I'm going to use animation to show this example. So if we use a naive method, it's going to pull the job from the queue one by one. Then it's going to allocate this blue. Blue means job 1, and yellow is job 2. And then once we finish these 2 jobs, we realize we can't put any other job into the system because of either CPU or burst buffer. In this case, the CPU is 4 because none of the job in the queue can be put, has enough space. Any other job in the queue actually has a resource requirement beyond what available. So if I look at this naive approach, CPU utilization will be 8. Utilization will be 22. Now let's look at the other approach. In this other approach, we look at the constraint, we look at weighted, we look at the bin packing. They are going to select the J1 and J3. When you allocate these 2 jobs onto the system, then the CPU is going to be 4, and the burst buffer still has some space. So we have CPU utilization 100%, burst buffer 67%. Are these good enough? In fact, all of them overlook one possible solution. What are the solutions? If we select J2, J3, J4, this is what happened. CPU utilization, we end up CPU utilizing 89% and burst buffer utilization 100%. If I compare, of course, if you look just a simple look at number, I know this naive is not good. What about these two? Are they good enough? Which one is better? Is the second solution better or the third solution better? This actually triggers us to think, what is better? In multi-resource, in optimization field, they have very important concept called Pareto Set. If I look at these three solutions and I draw them on this two-dimension space, X direction represents CPU utilization and Y direction burst buffer utilization. I have three solutions, solution 1, 2, 3. If I look at here, S2 and S3 belongs to Pareto set and S1 is not. So what is a Pareto set? Pareto set is a set of a non-dominated solution if no objective can be improved without sacrifice at least one other objective. For example, in this case, S2 is not because S1 is dominated by both S2 and S3. And S2 and S3 are not dominated or strictly dominated by any other. If I want to improve burst buffer utilization, then I have to sacrifice the CPU. So let's call this two belongs to Pareto set. So we can see that S2 and S3 form this Pareto set. S2 has a higher CPU and S3 has a higher burst buffer. They both are good in the optimization field. So what we start to think is that we need, when we do multi-resource scheduling, we need to identify Pareto set. And when we identify Pareto set, and then based on the site policy, they can choose the best solution from the Pareto set. So in order to do that, so our goal is to try to identify Pareto set. So our design based on three key parts. One is a window-based design, similar to what we did in the Power Hour scheduling, and that we formulated the problem into an explicit multi-objective optimization. We call the MLEO problem. And then we use a genetic algorithm to solve the problem. Okay. Here is the design. So the bottom shows the traditional batch scheduler. And the burst, we call it the burst buffer scheduler for this case. So burst buffer scheduler basically is built as a plugin to a base schedule, whatever scheduler you use based on the site policy. And then we have this as plugin. We design our part, design as a plugin part, and then this is going to be a window-based, means that it's going to select the first W job from the queue based on the site policy. And then we use a scheduling optimization. We optimize it into MLEO problem and use a genetic approach to solve the problem. And I need to point out that this design is, in this specific paper, we use a burst buffer as a second schedulable resource, but it can be generally applicable to Power as well. And then this is our MLEO formulation. And then basically we specify, we have a very specific objective here. One is the CPU, the other is burst buffer. And then of course we have string. This is a NP hard. And the window size, of course, going to impact your optimization degree. And then this one shows you if you have different window size, what are the time to solution. So we did this sensitivity study in the reasonable. And then how to solve this problem? We choose genetic algorithm because it can be used to approximate the true Pareto set. And the most important, it is easily parallelized. parallelizable, means that we can easily solve the problem in a reasonable amount of time. And then genetic algorithm, many people probably know that, so I'm not going to go through this detailed part. Basically, you can look at it here. I can look at this as a window of job, And then so here I can see that I have a window of 5 jobs, okay? And the job, for each, so in this is called a chromosome. So each chromosome consists of 5 genes. In this case, each gene represents a job in the queue. If I have a chromosome as 1, means that I'm going to select this job. If 0 means I'm not going to select this job. So I go through the genetic algorithm, go through crossover, mutation, selection. Every time when I go through this process, I separate the job into, I separate the solution into Pareto set or non-Pareto set. And then this will, at a certain time, we use a parameter to decide when we should finish the search. This will give us the approximate Pareto set. That's the basic idea behind this design. And let's look at, once you finally you identify a Pareto set, then what we need to do is select a solution out of this Pareto set. Okay, how to do that? So this is basic. I think we believe this is supposed to be a site manager's responsibility. Each site has their own policy. For example, in the previous example, whether you should focus on CPU or burst buffer, that's really site decision. So in our case, we use a very simple rule. When we calculate, when we solve the problem, give this Pareto set, we have 4 possible solutions in the system, in the set, and then we need to pick one solution. So in our design, we use a very simple rule. Now, it first choose the solution that maximizes the load utilization, which is S4 here. Now, in case if you have multiple, then we will choose the one at the front of the queue. Then we are going to do a trade-off analysis. We will compare this solution with other solution in the set. For example, we look at S1, it's going to decrease the CPU utilization by 10%, but increase the burst buffer utilization by 40%. Similar for other comparison. Now, in this case, then which one we are going to choose? In our design, we always choose the solution. That if the improvement on the burst buffer utilization is more than 2 times of the loss of node or CPU utilization. For example, in this case, we find that S1 and S3 both fall into this category. Now, in this case, then we will choose the solution with the maximum improvement. In that case, we will choose S3 because it's going to improve burst buffer more than anyone else, and also burst buffer improvement more than 2 times of loss of CPU utilization. That's our design, but it's site decidable solution. So you can choose other solution if you want. So how we evaluate this design? Again, we use a trace-based simulation. We evaluate with the trace from Corey and the Theta. When we choose these 2 trace, we want to capture both capacity computing, which is Corey, capacity computing, and Theta, which is capability computing. And then we also look at what are the burst buffer requirement. Now, on Corey, it has a burst buffer record. However, in Theta, we don't have this shared burst buffer. So we project what will be the shared burst buffer based on the organization or configuration of both Corey and Theta, and project, we're going to use this number. And then we look at the burst buffer requirement of Corey and the configuration of 2 systems and what are the requirements on the Theta. There's a problem. The problem is that if I look at both traces, they don't have sufficient burst buffer requests. There's 2 reasons. One is that some job has a burst buffer demand, but it's not recorded in the log. Second, that's a major reason. Burst buffer is a relatively new resource for user, and once the user get more exposed to that, we expect a more significant use of the burst buffer. But at this point, at the time when we do the study, we don't have sufficient burst buffer requirement. So what we did is that we generated 4 synthetic logs on each trace. And then this synthetic log, basically, we're going to increase the percentage of a job requesting burst buffer to either 50% or 75%. And their burst buffer request will be in different range. So if we look at this 4 different synthetic log per trace, we can see the trend from S1 to S4. We can see we have a weak to strong conflict when you have more burst buffer requirement. And again, we compare with many available system design for multi-resource scheduling. We look at the baseline, we look at the weighted. When you do the weighted, it means that you combine multiple objects into a weighted sum. You can either balance means that 50% of CPU, 50% of burst buffer, or you care more about CPU, or you care more about burst buffer. And then in terms of a constraint means that the one as an object, the other one as a constraint. In this case, constraint CPU means that we are going to maximize node utilization and put burst buffer as a constraint, and constraint BB is the other way around, and then bin packing, and the BB scat is our design. We look at both resource utilization, means that both CPU utilization and burst buffer. We look at average job wait time, and then this is the result. So I'm going to go through all this and then show you our overall design. So we look at a number of scheduling matrix. We use this radar chart to show the overall performance. So the idea is simple. So the idea is that if you have a large area, that means that you have better scheduling performance. We look at so we look at on top, we look at original log, we look at S2, we look at S4, and then we look at the query, we look at the theater. And then they have a different curve represent different method. The simple idea, large area, the better. If you look at all this design, the simple information we get is that overall showing that burst buffer or our BB scheduler achieve best performance, especially when in these cases. This is the case where you have a very conflict resource requirement between CPU and not buffer, burst buffer. So this is just a general information. If you're interested, you can look at our HPDC paper published last year. And then we go further by looking at, instead of just 2 results, can you do more resources? So we look at 3 resources, and so when you do 3 resources, the general framework of the system don't need to change. The only thing is that you need to add more objective. And then you can use the same way to solve the problem. And then we do this evaluation across multiple workload and the same result. So the overall takeaway that we got from this research is that when you do multi-resource scheduling, you need to consider all the resources in an explicit MLEO optimization way. This is essential. This will give you more ways to optimize your workload and scheduling. There's a lot of open issues. For example, we didn't look into this there's a more job coming, and this job are much more different. So how we address it? And if I pick up this one specifically. So all these existing solutions are either heuristic optimization based. Everyone talk about this magic of machine learning. Explore or see what are the possibilities that the machine learning can do to improve system scheduling. So currently our group is exploring reinforced learning to improve scheduling efficiency, okay? So anyway, so this is not my own work, it's done by my group, and this is my collaborator, and I'm open for any question.
If anybody has questions about this for the Keynote speaker?